In this presentation, we will identify basic network elements, understand the basic purpose and concept of subnetting, understand the concept of the protocol stack and the process of encapsulation, and understand the role of the data link layer sublayers. Networking allows computers to send and receive information between each other. In order for this to happen in an efficient manner, a defined physical and operational structure needs to be in place. There also needs to be a clear set of rules or protocols that allow clear communication to occur. The Ethernet standard provides the structure for both the physical hardware and the communication protocols, and continues to allow for further development of communication technology. The speed, efficiency, and flexibility of Ethernet has led it to becoming one of the most popular communication standards. The speed it operates at is more than enough for most applications. The cost of the hardware is minimal compared to proprietary systems, and the level of knowledge required for installation and maintenance is common to networking in general. Ethernet is generally a local area technology which operates on a local area network known as a LAN, usually within a single building. The LAN consists of a series of computers or devices connected together by a medium known as Cat5 or Cat6 Ethernet cable. All of the connected devices are known as nodes. Larger networks, known as wide area networks or WAN, are covered by other standards, although recent advancements in Ethernet have allowed it to span tens of kilometers. LAN topologies refers to the shape of the network. Star-shaped is the most popular as it is easily scalable and easy to troubleshoot. Extended star is 2 stars with a bus in between. A bus has a chain of end users. A ring topology would typically include optical fiber in the network. If we take the case of one computer talking with another, we can see that the user generates a digital signal in binary. Within this same machine is a network interface card, or NIC, which will convert the binary data into an electrical pulse. This electrical pulse is sent over Ethernet cable to the other user's NIC, where it is converted back into digital data to be displayed in the user's software application. The 4 twisted pairs of the Cat5 or Cat6 cable consist of 2 transmitters and 2 receivers, which allows both users to send and receive data at the same time. This is called full duplex communication. If the proper cable is not used, this can result in collisions, which will slow the network. In this case, Ethernet will use a common technique called CSMA/CD, which is Carrier Sense Multiple Access / collision detection. This method detects when 2 frames collide. The unsent frames are resent after a specified interval until they are received. Of course, the route between 2 users or nodes on a network is rarely that straightforward. There can be many devices which information must pass through before it reaches its final destination. The main devices are routers and switches, and they decide where the information is ultimately sent. The cable between these 2 devices is known as a segment. Ethernet is referred to as a non-deterministic protocol, as the route, and therefore the time taken, between the 2 users is not consistent. The main difference between routers and switches is that routers examine the IP address of the information, which sends the information in the general direction of a smaller network in the LAN called a subnet. The switch then examines the MAC address, which is the address of each individual NIC. Although the MAC address is unique to the NIC of the device, a different IP address can be assigned every time the device becomes active on the network. Every device in the network needs to have its own IP address, including switches and routers. The information is then broadcast to all nodes in that subnet. The correct NIC will be identified and the information will be passed to the application to be displayed to the user. Subnetting a large network into smaller networks makes the overall network operate more efficiently. A subnet is a physical group of devices. All devices on a subnet see all packets transmitted by any device on that network. The performance of a network is greatly affected during heavy traffic due to the collisions and retransmissions. Every device on a typical network will need an IP address, subnet mask, and default gateway to communicate. If you type the CMD command into your Windows search box, the command window will open. If you type ipconfig at the prompt, your computer should display the IP address of your device and subnet mask and default gateway for your subnet. Each IP address is displayed in dotted decimal notation and appears as 4 numbers separated by dots. Each number of an IP address is made from 8 individual bits known as an octet. Each octet can create a number value from 0 to 255. An IP address is 32 bits long in binary and is divided into 2 sections, the network section and the host section. The network section is used to identify the network that the packet is intended for, and the host section is used to identify the individual host on the network. But we need to know where the network section ends and the host section begins. The subnet mask is a 32-bit long address used to distinguish between the network address and the host address in the IP address. The subnet mask is always used with the IP address. The subnet mask only has one purpose: to identify which part of an IP address is network address and which part is host address. By this method, we can decide how many networks you have and how many hosts we can have on each network. In this example, the subnet mask has divided the IP address into 2 parts, the network section and the host section. The network section can be increased at the expense of the number of devices, or inversely, we can increase the number of devices on a smaller number of networks. In this example, the subnet mask is 255.0.0.0. To find out how many networks we can have, we can use a simple formula, which is 2 to the power of n. This means that the total number of subnets we can have is determined by counting the number of bits in the network portion of the subnet mask. In this case, there are 8 bits, so the formula gives us 2 to the power of 8, which is 256 networks. There is also a simple formula to determine the number of devices. This is 2 to the power of n minus 2. In this example, the subnet mask is 255.255.255.0. To determine the number of devices possible on each network, we count the number of bits in the host portion of the subnet mask. In this case, there are 8 bits, so the formula gives us 2 to the power of 8 minus 2, which is 254 hosts. Each device in the subnet will have its own IP address, so if a device in one subnet needs to connect to a device in another subnet, it will need to go through a router, as only routers can examine IP addresses. In this way, the router acts as a gateway to other subnets. The device will look on its own subnet for another device first. When it is not found, it will ask for the default gateway, which is the router, to find the destination IP address on another network. Within each machine, the data needs to be arranged so that each machine can understand each other. The rules by which the information is arranged are known as protocols, and this group of rules are known as the protocol stack. From the software application, the data passes through the layers until it is converted into a physical electrical pulse. It is sent to the receiver, and the electrical pulses are converted into bits and sent to the receiver's application and displayed to the user. Note that not every application will need to use every layer. The 7-layer stack is known as the OSI model. This stack arrangement ensures a standard communication process between each node from the physically attached hardware through to the software application and the end user. The stack can be roughly divided into the application layers and the transport layers. Each layer has its own set of protocols relating to that function. The physical and operational structure of Ethernet only occur in the physical and data link layers. There is also a 4-layer protocol stack called the TCP/IP stack. Microsoft has used this stack for operating systems since Windows 7. In this stack, the Ethernet functions occur in the network access layer. Although it's a different name, the functions are exactly the same. Each layer has a different name for its information that is put in the message. These are called data units. Each data unit from each layer is assembled together until it ultimately forms an Ethernet frame at the data link layer. On the receiving end, the process is reversed and the data travels back up the stack to the application layer. The process of assembling all the data is called encapsulation. As the message moves through the stack, it picks up more information from each layer, and this gets added to the Ethernet frame at the data link layer. This is then converted into physical bits and sent out across the network to find its destination. When the frame reaches a node in a network, the receiver first checks the destination address at the data link layer. If the frame is for this node, it passes the frame up the stack to have the frame unpacked and inspected at each layer. If the destination address is different, the frame is passed to another node for inspection. Longer messages are broken into separate frames, then sent along the connecting cable to the receiving nodes. An application will send data along with a header containing other layer details if necessary. This is streamed to the transport layer, where it is broken up into TCP segments and the details stored in the TCP header. The network layer creates IP packets with source and destination IP addresses in its header. This data is then encapsulated in an Ethernet frame at the data link layer with the source and destination MAC addresses in the Ethernet frame header. The Ethernet frame contains start-stop indicators. Addressing is used to identify the source and destination devices. The type of data is used to identify the upper layer protocol. The data contains the packet header, segment header, and application data. Error detection occurs in the trailer. The data link layer receives the network layer IP packets and assembles the Ethernet frames. It is divided into two functions: the logical link control, LLC, and the media access control, MAC, layers, each of which are a separate Ethernet standard. The LLC sublayer acts as a buffer to the upper layers. It is implemented in software and can be seen as the driver software for the NIC. The MAC sublayer defines the media access process performed by the hardware. Using two sublayers allows one type of frame to have access to different types of media. The 802.1 set of standards refers to wireless Ethernet. A wireless connection will receive a wireless NIC. There are three common standards for wireless data: 802.11, known as Wi-Fi; 802.15, commonly known as Bluetooth; 802.16, a point-to-multipoint topology known as WiMAX. Wireless connectivity is convenient, but it has its issues, which include coverage, security, and electrical and radio interference. The 802.1 wireless network uses a collision avoidance technique called CSMA/CA, which will send a signal to sense if the segment is free. If not, it will back off and start a random timer before trying again. Ethernet is the protocol most commonly used in local area networks. A LAN is just a series of computers or devices connected together by Ethernet cable, usually in a star shape, also known as a topology. Ethernet cable consists of 4 twisted pairs, which allows devices to communicate simultaneously, called full duplex communication. If this is not possible, a process called CSMA/CD allows the unsent messages to be sent again until delivered. A typical local area network will contain both switches and routers. Switches examine the individual device's unique MAC address, while the routers examine the device's IP address. Routers break the network into smaller networks called subnets. The subnet mask divides the IP address into the network portion and the host or device portion. Smaller networks operate more efficiently as there are less collisions and retransmissions. The OSI 7-layer model defines the process by which the information is assembled to be sent across the network. The information is stacked inside each other, like Russian dolls, until it forms an Ethernet frame in a process called encapsulation and sent to its destination. The data link layer is divided into the logical link control and the media access control. The LLC sublayer communicates with the network layer to assemble the Ethernet frame. The MAC sublayer will determine which physical or wireless media for the frame to access. Wireless Ethernet has three main techniques defined by the 802.1 set of standards: Wi-Fi, Bluetooth, and WiMAX. Common issues with wireless communication are security, interference, and coverage.